Okay.
Full screen. Maybe somewhere here. Maybe I don't know.
Try Ctrl L.
I don't know why it doesn't show the full screen. When I share only the presentation, it shows the
Entire screen. Maybe if you choose entire screen, does that?
entire screen.
Yeah. Or is that?
It's sharing 60 by 9, but the presentation of 4.3 lines.
I'm sorry, if you could go here in the dot, you may have options maybe. No.
Because it's something here.
Okay. Let's see the full screen then. PDF again. Yeah. Oh, there you go.
Okay. Okay.
Good. Okay. I think we should start, okay? Time is running out, right?
Yes,
Yeah.
we should start. Yes.
So check, hello online participants, do you hear us? Could you confirm? Those who are online, could you please confirm if you can hear us? Just give you a thumbs up or say yes or no, it would be great.
Yes, we hear you.
Okay.
Great, thanks for the confirmation. Yes.
Okay. If you want to.
Great. So I'll introduce you first and then come over. Just take a second. All right, good morning, everyone. It's the second day of its event today, so we're very excited to start our first session of the day. We have very interesting presentations today, so we'll be going through all of them as part of the sequence. So first we have Mr. Emmanuel Antonio Paredes. He'll be presenting his paper now. Just a few basic ground rules. We have 2 minutes presentation, but I'll be asking you to stay within 15 minutes. Okay. So at 12 minutes, I'll give you a kind of signal that you have 3 minutes left, and then you'll be finishing up in the next 3 minutes. So we have 5 minutes for questions and answer session. So for clarifications and all those things can happen in that time. All right. So I'll very much happy to welcome Mr. Emmanuel Antonio Paredes. The floor is yours. Please go ahead.
Hello everyone, I am Emmanuel Antonio Paredes. I am one of the authors of the article Fluid Simulation with Isotropic Pressure Segregation and Time-Dependent Tensor Fields. And now I'm talking about of my last works with the Arthur Gonzo Machado, Gilson Antônio Giraldi, and Marcelo Bernardes Vieira. And special thanks for LMCC and CAPS for resources to bring to me here. in general, the work
Maybe you want to use the mic. Sorry, take that here.
Maybe it's better for the one or two
So,
to use
is
the
it mic?
microphone.
Yeah.
Yes.
Yeah. So if you can use the mic, then the virtual presenter can hear you well. Right?
Should be
Hello?
okay.
everyone here.
Yes.
Okay. In one context of this article, uh, in a few years, we working with anisotropy fluid flow. Gaining the object of our work is to uh, control the fluid path through anisotropy medium, aiming to create effects for computer graphics. Sure. Uh, one way of this, one way of this work that ensures the deviate the fluid flow is through pressure and viscosity modulation. So we can control the fluid behavior through this. And to modulate the pressure and the viscosity terms, we use the second order tensor fields, and we can interpret it as space deformation. Uh, so we can control the flow through this space deformation by the second order tensor field. So firstly, we have a mathematical model we use. It is a different version of Navier-Stokes equations for incompressible fluid flow. So in this version, we have the tensor field T using the second order tensor field T that will deviate the gradient of E and the using as a diffusion tensor in the viscosity term. T, or I said, T is a second order positive definite tensor field, and F is the sum of the external forces. And P all terms is equal to the Navier-Stokes equation standard. One motivation of this work is the big factor responsible for deviating the fluid flow is the pressure, and the pressure the method we using not have an accuracy for the pressure field, give us worst approximation of the pressure. So one of the motivation is construct a better method to approximation the pressure field. So we use a modification of the X0 method that also has particle in cell method. The first one, the equation, is the advection equation. So we can estimate the position and the velocity of a particle P using the integration of the first the position. We can estimate using the integration of velocity, and the velocity we can integrate using the velocity we can approximate using the integral of acceleration. The first is the basic of physics. So in the U approximation, we have the integral of an, with an is an end acceleration field term, and it can separate as an implicit and explicit form from the fields has a we know. So a to the n has the viscosity and the pressure part, and both can separate at implicit form and explicit form. The implicit form we see as delta sigma and delta p. the implicit form of viscosity and the implicit form of pressure. Using these governing equations, we can rewrite delta sigma and delta p as the sum of implicit and explicit part. So delta p is defined as T grade P minus Tn grade Pn. So we have the explicit part is the sum of all gradient P until since the beginning of the simulation until the last step, and T and Pn is the actual step we calculated. Okay, to approximate this particle velocity, we have the actual the last velocity of the particle plus implicit step a double hat plus integral of the explicit part a to the hat. Okay, so the implicit part we're using a double hat, we can calculate using delta sigma and delta p, and the explicit step we can calculate using all the velocity, pressure, and explicit forces we already calculate. For the first step, we have the initial conditions. So to calculate the explicit part, we use the third order Range-Kut scheme, it's shown in the slide. When I have an integration of Q, where f of Q is the derivative of Q, and Q is and Q represents the position of the velocity. Maybe other quantities you integrate in the time. Okay. The first velocity approximation, we're using the explicit part. So the first velocity approximation of the particle velocity you have, we can find using the integration of the implicit part a hat. And the second velocity approximation we can reach through the viscosity form. So we can calculate delta sigma, and as the unknown, u hat n plus 1 u and whole the position x we already have. So the only unknown is delta sigma. So we can calculate the second velocity approximation u double hat through the first approximation of velocity plus the delta sigma we already calculated in this step. Okay, we already talking about the viscosity, but now we're talking about the pressure step. So the implicit form we already put in the slide, where we have the gradient of, the Laplacian of delta p is equal to the difference of double hat u. We expand delta p, we have gradient of p n plus 1 and as an unknown, and the left hand and the right hand side we have p to the n. We already know, and the last step. So this is a linear equation, and this is a partial differential equation, but we can approximate as a linear equation, linear system equations, using finite difference, volume difference, finite elements, or all types of methods. But in this work, we focus only in the expanding all the equations and solve only the pressure step, the um, the viscosity step we don't discretizate. So we only solve um, like a Euler equation without the viscosity. So in this step we calculate delta P using the gradient of P or Pn plus 1 and gradient of Pn. So to the velocity particle, we can calculate the divergence-free velocity approximation from the velocity particle the velocity particle using the second velocity approximation and the delta P we calculate already. So to update the velocity particle, we also ensure the one more modification in the X-Sivas normal method. We don't have this modification. This modification in the original method, alpha is equal to 1. So the velocity particle is equal to the velocity we calculate in the last slide. However, we ensure the free propagating in this step to reduce the velocity dissipation. The X-Sivas method has a better approximation of pressure, however, is velocity dissipation so high, like a big method, however, not so smooth. It is a better approximation, but is it's already too smooth. So we ensure the Philip updating as linear interpolation of the solution of the implicit and the explicit the implicit and the explicit parts of the method. Okay, the experiments, we can see the first experiment in the article. We have one experimentation. In the start of the experimentation, we have one hole in the middle of the bottom of the tensor field. So we release the simulation, and the pressure goes made the fluid made the fluid up to in the middle, but in the second step we release four holes to the corners of the bottom and release again the pressure. We can see using alpha equals 1, we have the X-Sivas method, standard method. Gas, sorry, the X-Sivas method, the standard X-Sivas method. Okay, so smooth the dissipation of velocity so high. You can see with the next frame, using the alpha equals 0.15, we have less dissipation than the last. We have less dissipation compared to the last slide. So in the slide you can see how the flip update in the final process can released uh, a better approximation of the velocity. However, that series has the better approximation of pressure. For conclusion, uh, we we build a more accurate numerical method using the x-zebras base, but uh, have a crucial problem in the original mathematical model that is not have conservation of momentum. In the in computer graphics, maybe is interesting because we can create zones of accelerating and decelerating the fluid, creating different effects. And one future work is we need to create a model to project significant tensor fields. How we build a tensor field to do what you want. So is a challenge too. So for future works is one suggestion. And thank you for your attention.
Great. Thank you, Emmanuel, for keeping the time up. Thank you for that. So now I would like to invite questions from the virtual presenters. So please let me know if you have any questions. And if you have, please unmute your mic and please go ahead and ask the questions to Emmanuel. For online participants, do you have any questions for Emmanuel? All right, if not, definitely we're going to have a chance to talk to our other participants in the tea coffee break. So please do continue the discussion. All right, thank you very much. Great. Now let us move on to the next presentation, which will be done by big co-authors and authors. So we have Joao Bitter, Israel Mendonca, Glauco Amorim, Digor Brandao, Anna Pereira, and Pedro Gonzalez. So I'd like to invite our second presentation online. Please go ahead, unmute your mic, and share your presentation to the virtual mode. And just to make sure, we keep on time. As I told our first presenter, please stick to 12 minutes presentation, and I'll give you 3 minutes warning before that, and we will have 5 minutes towards the end for Q&A. All right? Thank you.
So can I share my screen?
Yes, of course. Yes, share the screen.
Yeah, I'm sorry. Could you kindly share the screen with us?
Yes, I
Okay.
Okay, sure. Let us know if you need any help with that. Okay.
could you see?
Yes.
Can I start?
Yes, of course, you can start. Thank you.
So my name is João Vitor, and my wife is Dias Carneiro, and I'm a master's student in computer system engineering at the Federal University of Rio de Janeiro. I'm gonna present my work about multi-centrality risks for the bandwidth reduction problem. And this is the authors with work with me, with Alme Donson, Glauco Amorim, Sanderson Gonzaga, Ana Isabel Pereira, Diego Brandão e Pedro Henrique Gonzalo. This summer, this work is divided into the introduction with a brief motivation, and then I will talk about the problem description, then following with the relevant related work, and then I will talk about the multi-intelligence heuristic algorithms that we propose in this work. And then I will talk about our computational experiments and then conclusion and future works. Many simulations in science and engineering require solving extensive sparse linear systems, often representing their highest computational cost. By concentrating all non-zero elements within a slim band around the main diagonal and employing a rewarding matrix, efficient gains in operations like inversion and determinants can be achieved, resulting in a lower computational cost and time saving. In this example, I can we can see how a space matrix instance behaves before and after bandwidth reduction using the Kucher-Maki algorithm for such a reduction. That is a that's where this algorithm is a no algorithms in the literature. So in certain cases, it's interesting to view this problem as graph labeling, where it represents a space matrix, and it's a figure we can see that the bandwidth of this graph is represented by the difference between the label of the vertex 4 and the label of the vertex 5. And the this is and we can represent a space matrix in a graph. We how we can see this figure. So when we change the vertex 1, the label of the vertex 1 for the change for the label of the vertex 4, we can re- we can reduce the bandwidth of this graph, and consequently we can uh, we can uh, represent by the we can represent um, we can obtain a new bandwidth represented by the difference between the label of the vertex 3 and the label of the vertex 5. We can I see in this picture. So the relevant is related work. I studied focused on low computational cost risks concluded that the variable neighborhood search methods in demonstrating better effectiveness in bandwidth reduction, for instances from the switch sparse matrix collection. And the table we can see how the most promising heuristic method for the bandwidth in the last decades, in the last decades since uh, s- mm, 1690. The algorithm now I talk about the algorithms that we proposed. So the algorithms initialize receive a array of centrality for each vertex, then initializes dictionary to mark the visited vertices. After that, breathed first search vertices are placed in rows as follows. The first row contains only vert k that was chosen randomly. How can I see in the line 5? And label 1 is assignment to each vertex adjacent to k are in the second row, and their vertex is labeled in the order of centrality. performing a grid procedure. The third row contains vectors not included in the previous rows but connected with vertices in the second row and so on. And the second part, in this part of the algorithm, is responsible for the random call of centralities. So this algorithm combines the flexibility of multiple random calls for the initial choice of the first vertex to be labeled by the algorithm with the diversification provided by selecting different centrality mixtures. So the idea is that diversified centralities can guide the construction of the solution in various ways, exploring several aspects of the graph's structure. So we can ask which centrality to choose. Before conducting the experiments, it was essential to identify the centralities most pertinent to bandwidth reduction. The methodology adjusted the Cutting-Mackey algorithm by modifying the criteria for selecting the labeling order based on various centralities from existing literature, I mean to assess each centrality's impact on bandwidth reduction. Each select centrality was implemented with two labeling orders, one for the lowest to the highest degree and another for the highest to the lowest degree. The table implementation choice for each centrality based on the highest reduction achieved. The result that is we can see in this table 2 and 2. We analyzed the relationship between bandwidth reduction among various algorithms, focus on correlations of zero point 0.8 or higher results. And figure 2 visualizes this correlation with vertices representing centralities and edges indicating correlations above the threshold. To remove redundancies from centrality was formulated is a minimal domain set problem solved using binary integer programming. After that, the chosen centralities we degree we degree and engine with the solution of the binary integer problem. We implemented the now I will talk about computational experiments, and the experiment was implemented the method was implemented in Python 3.9 and executed each time 10 times for each instance on an Intel Core 11th generation processor i7 with a frequency of 2.8 gigahertz and 16 gigabytes of RAM. The set of matrices used in this work is a set of 43 instances from the suite Space Mythicus collections. When I decided the two better centrality for the algorithm, we decided mm, make three versions of the algorithm, the risks. And the first version is a constructive method using degree centrality. The second version is the second method employs the centrality of engine vectors as the basis for vectors labeling decision, and in the third version the method implements a random call approach with both centralities. We executed each version 10 times for each stance. Initially, the third version, the multi-centrality tree version, showed apparent superiority over the other versions. So after conducting the initial experiment and the execution, execution, execution time was favorable, we sought to measure algorithms in the literature that had a time of less than zero point 0.5 sec to compare the results obtained by the proposed methodology with low-cost risks. We can see in this graph the multicentrality risks gain number of instances with best reduction about the Kuchihoma key and constructive VNS that's present in literature. And we can see too the comparison of time between risks in seconds because there is many risks in the literature that gain a best reduction, a good reduction, but average time uh, is too long. You expensively cost computation. The result, conclusion, and future works. The result presentation in this work focus on developing and evaluation a new multi-centrality constructive algorithm for bandwidth minimization in space meters. Our computational experiment revealed that strategies implemented with a relatively simple construction procedure can outperform no algorithm used in practice for bandwidth reduction, such as Kuchihoma-Ki. In particular, the reset procedure based on random centrality choices confirmed the benefit of encouraging diversification of this study. Based on the results presented in this work, a possible direction of study is implementation of hybrid versions of the VNS band. An additional approach would be to implement a machine learning classification model in the instance preprocessing, allowing for analyzing of the behavior of reduction with different centrality strategies per instance classes. That's it. The author would like to thank from Brazilian Genesis, and this is my reference using this work. And thank for your attention. Does anyone has any questions?
Sure. Thank you very much for keeping your time and nice presentation. Really insightful. So I'll have invite questions and comments on this presentation from the room. Anyone have any questions? Okay. From the virtual room, any questions for the presenter? I can see Mikhail is there. Samantha, any questions for our presenter here?
No, I don't have any specific question. I want.
All right, great. So let's continue the discussion in our interactions with other patients. Thank you for your nice presentations once again. So
Thank
let
you.
me now move on to our third presenter, which is Nezada Firza. Are you here on virtual platform? No. No. Okay, I don't see she is online. So let us move on to our next presenter. And they are Simant Mondal and Rajiv Chandra Ghosh. So please share your presentation online and then start. Again, just to recap the norm of the presentation. So I'll be stopping at 12 minutes, and you have 3 minutes more to stop the presentation. I would like to have remaining 5 minutes for Q&A. But since we don't have any much questions in so far this morning, so you might want to use also the whole full 20 minutes for your presentation. Thank you. The floor
Okay,
is
understand.
yours.
Okay, so can I share my screen?
Sure, please go ahead.
Uh, is my skill visible to everyone?
Yes, please make it full screen so you can see
Sure.
the.
So I am Shimanta Mandal. Currently, I am doing my masters in the University of Naples Pedrico too, and I am doing my masters in data science. So today I'll be presenting my paper titled "Study on Different Parameters Affecting the Overall Cost of Global Content Distribution Services in Metropolitan Cloud Network." So this is the introduction part. Coming to the introduction part, we have tried to compare the different cloud augmented network services. So where we have compared four different services. These services are like professional video on demand like Netflix, then professional live video like IPTV, then user generated video on demand like Facebook, and user generated live video like live Facebook streaming or YouTube streaming like streaming platform. And we have tried different parameters like the rate, the overall cost, how these parameters are having an effect on the overall cost of the network flow of the cost in the network. And we try to build an optimization model to minimize the overall cost, also the minimize the overall uses of the different resource blocks in the capacity resource block, so that the overall capacity of this network is reduced. And this is the formulation of our cloud network flow. I mean, this is the uh, overall formulation of the of our optimization model. So I don't think I have much time to explain each and every equations that we have used for the final formulation, but I just tell something about the objective function. Here our objective function tells that the main purpose of that model is to reduce the cost and the delay. So the left hand side, it is about the overall cost, and the right hand side of this formula is about the delay. So if the objective function is related to the minimization, reduction of the overall cost and the delay of the content flow or the content delivery in our cloud in the cloud network. So we have used different constant like for conservation constant, chaining constant, source constant, and other constant to develop this final optimization model. So here we have considered three different network, and this is our fast network. And in the fast network, there is a single source and multiple destination. Here, the blue ones are the source, red nodes are the destination, the black ones are the communication node, and the purple ones are the computation node. And this part is the core, and this part is the edge, and this part is the access layer. And this is our fast network, the cloud augmented network. And then this is a service graph. So actually the service graph tells how what will be the technical configuration of our original cloud network. So this cloud augmented network tells how different components are interconnected with each other, how they're going to communicate, and how the total network will operate. I mean, how the network content will be flowing from the source to destination to this network. And the service graph tells about the technical configuration. I mean, how the commodities will be and the objects will be. And this is the second network, which is the advanced version of the network one. Here the difference is that initially in network one there is a single source and three destination. Here there are single source and 14 destination, and there are four access node associated with each edge node. And the next one is the advanced or modified version of network 2, that is network two-way. Here what we have done is we have just add a computation node at the access layer, just to check is there any impact of addition of an extra computation node of a in the access layer, to check is there any impact on the overall cost of this extra computation node on the access layer. Here the service graph is also the same. Here there is a single source and 16 destination. So here there are 16 destination. There are 48 commodities and 33 objects. And but we have also used here overlapping. Due to the overlapping, as the content are same from the source, the objects are here 33. So this is the actual convention how the network is flowing. The plot is shows how this is the source. 30 dot is the source, and the 49th is the destination. So this shows the convention that we have used throughout the slides. How the content is flowing from the source to destination. This is for the source commodity. This is for processing and caching, and this is for the destination commodities. So here for each of the network, we have considered four different services. So for there are three different networks, and in total there are four services. So there will be 12. There will be in total 12 services, but it's not due to the time constraint. It's not possible to show all the services. So I will be showing only a single services from each of which are associated with each of the network. So for network one, I will be going with the professional video on demand. That is Netflix. So here there are two different cases. Here there are communication link and computation link. So here the communication link capacity is 5 Mbps, and total number of resource block here is 200. So the actual capacity of this communication link is 1 Gbps. And here the rate before the caching is smaller than the rate after caching. So here you can see as the capacity is 5 Mbps. The caching are happening at the edge, because we don't have mass capacity to do the caching at the core. So the algorithm by default selecting the AS to perform the caching and processing. Whereas if you jump to the case 2, where the communication link capacity is increased to 50 Mbps, then you can see the caching are happening at at core, and they are overlapped, because now we have sufficient amount of communication link capacity, so that the content can pass from the core to is just using a single resource block, that is 50 Mbps, and the content uh, uh, is the size of 50 Mbps. So here there is a use of only a single resource block. So that's why in case 2 we can see the caching is happening at the core instead of happening at the edge, like case 1. So here you can see for the case 1 the cost was 4026, which is reduced to 700 200 in case 2, just by increasing the resource block capacity. And here, one interesting thing is to check is we have done a comparison between the rate and cost, which is really obvious. If rate increases, the cost, the overall cost of the network will also increase. But here, one thing is that we have fixed R3 as 50 and R2 also 50. We increase R1 to check what is happening actually. So we see from 15 to 45 all the time the caching is happening always at the edge. But when R1 becomes equal to R2, that is 50, the caching are overlapped and happening at core. So from these, we can conclude a point that uh, if there are sufficient amount of capacity of the resource block, like communication resource block, there is a high tendency that the caching will be happening near the source, always near the source. But the condition is, the constraint is that there should be sufficient amount of capacity. Now this is for the network 2, and the service is professional live video, that is IPTV. Here we have considered three different cases. One is 5 Mbps case, 50 Mbps case, and 200 Mbps case. And here there are single source. The source is at A0, and the destinations are at F1, G1. These there are 16 destination and a single source. So for the 5 Mbps case, we can see the same as the previous one, but here one difference is there, that is the rate before caching and rate after caching is different, is same, sorry, is same, and rate after processing is higher than the rate before processing. Why? Because for professional live video, like some online streaming, there might be some sort of improvisation of some specialized or personalized advertisement after processing. So that's why we expect to have a greater or a higher rate after processing. That's why R3 is greater than R1 and R2 here. So here we can see the same thing, that is caching and processing are happening at the edge, and source is at the core and destination is at the access layer. But when we jump to the case 2, sorry, case 3, that is 200 mbps, when you increase the communication link capacity as 200 mbps, then we can see that now caching are happening at the core. That means now we can utilize the power of overlapping. That is nothing but reducing the uses of resource block, and ultimately the outcome is the reduction of the overall cost of the network. So here you can see for the case one, the overall cost was 19,288. For cost for case two, it was reduced to 4,088. But for case three, that is 200 Mbps case, the overall cost of the network is only 2,475, and also the number of links used are less than that of the use of link in case one and case two. And this is for our last network, that is network 2A, and the service we are going to explain is user generated video on demand. And here, what is the difference between these user generated video on demand and professional video? So initially, for the professional video, the source was at the core, but for this case, both the source and destination will be at the access layer, because here users are the generator of this content, and the users are only consumer of this content. So here we can see there is nothing at the core, all the things are at the access. Or also in network 2A, we have added one extra computation node at the access layer here. So we can see that now for case one, all the things caching and processing are happening near the source only. So as we have already mentioned, if there is sufficient capacity, there is a tendency that the caching will be always near the source. Here we can see the proof again. And for case 2, when this is 50 mbps, then we can see caching and processing are overlapped at edge. That is resulting a reduction of the overall uses of resource block. So here also you can see for case 1, case 2, there's a huge reduction in overall cost, as the number of links are reduced, and number of resource block users is also reduced from case 1 to case 2. So as I don't have much time, so I'll directly go to the comparison of these different services with respect to network 2 and 2A. And we have considered 4 different parameters that are communication resource block uses, computation number of computation resource block users, the total cost, and maximum delay. And we have considered 3 different cases: case 1, case 2, case 3. That is 5 mbps case, 50 mbps case, and 200 mbps case. Instead of just looking at the table, I think it will be better to visualize this thing using that graph. So here it is the dual axis graph, and the x-axis is resource block capacity.
Because practical difficulties. A significant reduction is in uncertainty, and hence an increase in localization accuracy can be achieved by incorporating information about the signal propagation environment. This approach requires knowledge of propagation environment in each specific case, as well as a complex mathematical models that simultaneously account for an arbitrary environment in homogeneous and measurements. Significant progress in this field has been achieved in computational hydroacoustics, where such inhomogeneities as sound speed profile and sea bottom uh, can be used for the source localizations and for some environment inversions. The aim of this study is to investigate the possibility of localization in conditions where the diffraction and multiple reflections have a significant impact on the wave propagation. Let's start with the schematical problem statement. We have several thin vertical impediments called knife edge. They are impenetrable for the waves, as well as we have the impenetrable underlying surface. We know the positions and the heights of our knife edge, and also we have several point receivers with also known positions and complex amplitude of the wave meshed by them. The wave field is generated uh, by the source with an unknown uh, with unknown position and its power. So the task is to find the position of the source and its power. Okay, let's move on to the mathematical problem statement. In this study, we consider two-dimensional Helmholtz equation, but this approach can be also applied in three-dimensional case. We are given m knife h with known distances and measurements with known positions and complex amplitude. And the task is to find XS, which is the position of the source. Okay. th- The most commonly used approach to all kinds of such inverse problems is the matched field processing. Here we formulated using the adjoint method. We consider Hilbert space with color product, define an adjoint operator. Then we suppose that we have some measurement device that measures certain integral characteristics of the field. In a simple case of delta um, delta receivers, uh, it can be simplified. Uh, so you can see that our task is reduced to the following equation. But of course, it is clear that the solution of this problem is not unique. As we will see later. And also, it is clear that the solution of inverse problem is based on several solutions of several forward adjoint problems, which are almost the same as the forward problem. So next we consider two well-known matched field processing processors. First, we define the two vectors. The first vector correspond to measurement data, and the second vector is a green function where each each row correspond to the solution of the joint problem from one of the receivers. So we can formulate our problem um, as a following minimization problem, or we can write it as follows. Another approach is a minimum variance process, which is also defined as depicted. Now let's briefly discuss the forward problem. Generally speaking, it is essentially two-dimensional and quite computationally expensive. Here we use a recently proposed by me and Professor Pavilov method, uh, uh, which helps to reduce the multiple knife edge diffraction problem from a two-dimensional problem to a system of one-dimensional equations. Its size is equal to a number of knife edges, and it should be noted uh, it should be noted that it can be computed numerically very very efficiently, and for for details the link is given. So now let's move on to the numerical results. First, let's discuss the flow and the algorithm. Of course, it is quite difficult to collect real measurement data for such a model problem. So we use simulations. First, we compute two-dimensional field distribution from the source. It is depicted on the left figure in each example. Left figure. Next, we choose a space point corresponding to the receiver locations. Here we can see the vertical array of receivers. And the field value at the points is used as a measurement for forming the vector v of the measurements. So we also can see this. Next, we compute n two-dimensional adjoint fields using the method from the previous section. And it gives us an opportunity to compute the vector field function g, which is a green function valued vector. Next, we use it to compute the ambiguity surface using the two methods, Bartlett and minimum variance. The two-dimensional distributions are shown on central and right figures. We can see them. And finally, we found a point with the maximum value, and this point will be the location of the source determined by the method. So first we consider the propagation, and in free space we only have an underlined surface. We pose the source at the height of 50 meters, and we have an array of receivers. So let's suppose that we have only the values on the receivers, and we don't know the position of the source, and we want to determine them. As we can see, both methods correctly determine the set positions. The Bartlett method provides a more spread out solution. in space. However, uh, the maximum coincides precisely with the location of the actual source. So let's pose one knife edge behind the source location. Here we can also see that both methods correctly determine the source position. And we can see that on the array there is not only the transmitted field but also uh, the reflected field from the knife edge. So the less ambiguity in the Bartlett method. Next, we can see the non-lined of sight case. We can see there is no line of sight between the source and the array of receivers. Here, the Bartlett method exhibits greater uncertainty behind the obstacles. Nevertheless, its accuracy determined the, the location of the source. However, the minimum variance method, despite the absence of uncertainty, incorrectly detected the source of radiation. Next scenario, we consider the source and receiver located between two obstacles. Besides diffractions, the effects of multiple reflections between obstacles are significantly pronounced in this example. As we can see in figure, even in the complex conditions, both methods generally correctly determine the position of the source. And in this example, we consider a horizontal array of the receivers. We can also see that both methods uh, achieved a good results for the vertical array of receivers. And finally, we consider a complex examples of four knife edges. We can see for knife edges multiple complex propagation effects, but as we can see, but Bartlett method achieved the exact result. Minimum variance method killed some error, 23 meters in range, but generally it's also correct. This is a summary of 6 examples. Uh, it is evident that the Bartlett method perfectly determines the search positions in all cases. However, the mean variance method almost always yielded results with some degree of error. So it should be noted that the main aim of this work was to demonstrate the possibility of precise size location simultaneously in conditions of interference, diffraction, and multiple uh, reflections, and this aim was achieved. Uh, in this study, we considered only a model example with knife edges, but in future work, it is reasonable to consider some more complex scenarios, such as propagation in complex uh, uh, urban conditions, consider more complex obstacles, and so on. And finally, it should be noted that the source code is freely available on my GitHub repository. So, I I warm welcome for users and contributors to participate. Thank you for your attention.
Great. Thank you, Mikhail, for the nice presentation. It's really interesting. I leave the floor now for questions, comments, both from online participants and also here in person. Any questions? Virtual participants, any questions for Mikhail? All right. If not, then thank you everyone for sharing your thoughts and research outcomes to the session here. And definitely, this is not the end of it. So I would like to encourage you guys, those who are meeting online, like see here, Simanjal on the fingers. Please keep in touch with all others so you can help in terms of collaborating and understanding these outcomes. Because we are very much open for networking and understanding what you do, regardless of what geographical locations. But it's important to understand what you do for research and how do you come up with these outcomes, right? So let's keep in touch with networking options, and then definitely ICSA is a very wonderful platform where you get to meet all those your peer doing research in your areas. So let's keep an eye on those, and then keep going with your research, and then I wish you all good luck for your future endeavors. With that being said, I would thank you, Sarah, for your very good help this morning with us. And thank you for you all participants for your nice presentations. And I wish you good luck in your future endeavors. Thank you.
Thank you.
I think we're
Okay.
good to go.